By the time you breathe once, or you listen to each word in this sentence, a few million particles would have passed through your body and further down through the earth without leaving any trace of their path. All these particles pass through the universe at the speed of light. One of the many types of these particles are called neutrinos, meaning little neutral ones. To get an insight of neutrinos, we need to travel back to the beginning of this universe. Developing our understanding of the universe we live in has taken many years, with many twists and turns in the story. Scientists believe that this universe was created in a powerful explosion called the Big Bang about 14 billion years ago. All the particles, including neutrinos, were produced in that gigantic explosion. There were other interesting particles too, which now pervade the entire universe. We all are always curious to know about our existence. So how could neutrinos help us to understand our origin? To better understand neutrinos, we need to know what the objects around us are made of. All things that we see around us are made of atoms. An atom consists of a nucleus containing neutrons and protons. Electrons go around this nucleus. An electron is an elementary particle. By elementary, we mean that they cannot be divided further. Scientists have discovered that electrons have two cousins, similar in behavior but heavier. They are the muon and the tau. Like the electron, neutrinos too are elementary particles. But unlike the electron, which has a negative charge, a neutrino is chargeless or neutral. Neutrinos are denoted or represented by the Greek letter nu. They come in three flavors, namely electron neutrino, muon neutrino, and tau neutrino. This fact is of significance, and we shall go into depth later on.
Actually, neutrino is the second most abundant particle in the universe, the most abundant particle being photon, the quantum of light. Although neutrino is present in the universe in such large number, till recently we knew very little about their properties, how they interact and so on. This is because it is very difficult to detect and study neutrinos. They hardly interact with matter.
Unlike most other particles, neutrinos are able to escape from dense regions such as the core of the Sun.
And neutrinos are also very important for our life itself, because if there were no neutrinos, sun will not shine.
This is what makes them of interest to scientists. Neutrinos are abundantly found in nature, as the Sun and similar stars and supernovae produce millions of neutrinos every second. They are also produced as a result of cosmic rays interaction in our atmosphere. They are also produced in radioactive decays and in other man-made processes like nuclear reactors and particle accelerators. Neutrinos were initially thought to be massless. However, recent experiments have resulted in groundbreaking discovery that neutrinos change their flavor as they travel, and this changing of flavor is termed as neutrino oscillation. Scientists know that neutrino oscillation can happen only if neutrinos have mass. This property of neutrinos is of great importance in using neutrinos to probe the universe in particle physics, cosmology, astrophysics, and also to probe the core of the Earth in geophysics. This study of neutrinos is important and exciting because they are one of nature's fundamental particles of which we know little about. There are other mysteries in the universe that can be answered by using neutrinos as probes. Post the Higgs boson discovery, popularly known as the God particle, scientists look towards neutrino experiments for clues to understand the complexities in the universe. Many countries have taken initiatives to set up experiments to study neutrinos. The Super-Kamiokande Neutrino Observatory in Japan hosts one of the prominent experiments. It was here that a neutrino oscillation was proved and was subsequently awarded the 2002 Nobel Prize. The Sudbury Neutrino Observatory in Canada is similar to the Super-Kamiokande. The Gran Sasso Lab in Italy is the largest underground laboratory in the world for experiments in particle physics, particle astrophysics, and nuclear astrophysics. They run many experiments, including neutrino physics, in their underground lab. The IceCube Neutrino Observatory, or simply IceCube, is a neutrino telescope constructed in the South Pole. The detectors are optical sensors inserted deep inside the Antarctic ice. When neutrinos interact with molecules of water in ice, they produce signals which are picked up by the detectors, and these are then studied. There are still other experiments like MINOS, Diabe, etc., each one trying to understand the different aspects of neutrinos. The experimental field of neutrino physics is now moving into a phase where decisive and high-precision experiments are needed. It is in this context that an initiative began to take shape a few years ago, leading to the idea of an India-based Neutrino Observatory, or the INO. Now that we have a brief idea of neutrinos, let's take a look at the history of neutrino experiments.
Neutrino research is not new to Indian scientists. In fact, the first ever cosmic ray neutrino was detected in an experiment at Kolar Goldfields in a deep underground lab in 1965. However, since the neutrino field has become a very exciting area of research, the Indian scientists are thinking of starting a new laboratory, underground laboratory somewhere, to study neutrinos again. This is one of the biggest high energy physics project, or you can say biggest experimental project in the country right now.
So let's understand how we can detect neutrinos at the INO.
The primary aim of the neutrino detector in INO is to study the atmospheric neutrino oscillations. It will determine the neutrino mixing parameters precisely and also address the question of neutrino mass ordering. The chief feature of this detector is that it can distinguish between neutrinos and antineutrinos. About a kilometer of rock is needed to filter away cosmic rays so that the detector can become sensitive enough to detect the neutrinos.
Only neutrinos and some very energetic muons can penetrate more than a kilometer of the Earth's rocks. So, neutrino detectors are mostly located under a mountain or in a mine so as to filter out cosmic rays. After surveying several sites, the West Bodhi Hills in Theni district, about 110 kilometers from Madurai in Tamil Nadu, has been chosen for this project. Geological, seismic, and environmental factors all favor this place. The proposed lab is under the mountain and will have 3 interconnected caverns that will house the 3 main experiments, besides areas for services, electronics, control room, etc. A 2-kilometer long motorable tunnel will connect the caverns to the outside of the mountain.
The flagship experiment of the INO project is a massive 50 kiloton magnetized iron calorimeter, or ICAL.
The ICAL will consist of particle detectors called resistive plate chambers, that is RPC, arranged in between 56 mm thick iron slabs. The ICAL is a giant 150 layers sandwich of alternating layers of iron and RPCs weighing 50,000 tons. One purpose of such a large quantity of iron is to offer densely packed iron atoms in the path of neutrinos and other particles. The detector can measure the energy of the particles, hence the name calorimeter. Over 30,000 RPCs will be used in this detector. The size of the RPCs would be similar to 4 carom boards placed in a square fashion.
About 3.6 million channels or wires will carry electronic signals from the RPCs, and finally the data will be stored in a computer. A sophisticated electronics, data acquisition, trigger, monitoring and data network systems are being designed specially for this experiment.
One unique feature of the ICAL will be its ability to distinguish between neutrinos and antineutrinos. For this purpose, the ICAL will have the world's largest electromagnet, consisting of current-carrying coils that will magnetize the iron of the entire detector. Just as a telescope observes the sky through visible light, the ICAL will observe the sky through neutrinos. Similarly, the ICAL can also look towards the core of the Earth.
The magnet, which is 52,000 tons, will be the biggest in the world after it is constructed.
The weight of the ICAL is the weight of about 10,000 elephants. The area of the ICAL would be the area occupied by about 160 Tata Nano cars. The laboratory will also host several other experiments such as neutrino-less double beta decay, which would shed light on the nature of neutrinos. It will also host an experiment for detecting dark matter.
Neutrino-less double beta decay experiment will test the true nature of the neutrino. This experiment will be set up in the control room cavern of the INO tunnel. We will be making a detector with 124T nucleus. When it undergoes a double beta decay, the 2 electrons will be produced, and we are making a detector to precisely measure the energy of these 2 electrons. This bolometer detector will operate at a very low temperature, which will enable the measurement of the energy of electrons very precisely. At present, the group's effort is focused in developing such a low temperature bolometer in our lab at KIFR.
Dark matter experiment is also planned at the INO complex along with some more futuristic scientific programs. The INO will not only be a neutrino observatory. In the long run, it will host other experiments related to geology, biology, among others. Outside the hills, surface facilities like housing for scientists, engineers and other workers, hostel for students, labs, offices and workshops will be constructed in the available land.
So it's of a scale which is different and large and ambitious, and I think it's something that it's great to see that scientists in India, I mean this is a national effort of course, and it's great to see scientists in many institutions collaborating on this important scientific endeavor.
At present, there are various institutions in India which work in different areas of the experiment. At the Tata Institute of Fundamental Research, TIFR in Mumbai, a prototype stack consisting of 1 meter by 1 meter resistive plate chambers, that is RPC, has been developed and is currently recording cosmic muons continuously. The electronics required for the setup is designed and tested by scientists and students. About 30,000 RPCs of size 2 meter by 2 meter will be used in the actual experiment. These RPCs will be finally manufactured by the industry. A special lab has been set up at TIFR for developing and testing large area RPCs and characterizing them. These are done by students of the INO graduate school as part of their coursework. They are also trained in making these RPCs. Other institutions like the Bhabha Atomic Research Center (BARC) in Mumbai and the Variable Energy Cyclotron Center (VECC) in Kolkata are involved in designing of the magnet for the experiment. Another prototype stack with the magnet is currently in operation at VECC. Apart from electronics and the detector studies are also conducted on gas recirculation systems. The RPCs are filled with a gas which helps detect particles passing through them by producing an electric signal. Thus, the gas mixture is a crucial component in the detector. The RPCs have gas inlets through which the gas enters the detector and gas outlets through which gas exits the detector. The gas that comes out can be further purified and recycled by an efficient gas recirculation system. At TIFR, various activities related to the development of a gas recirculation system are being undertaken. Simulation.
We are going to build 50 kiloton of these detectors, and to build it we have to be sure that what our physics goal, this detector will satisfy that physics goal. And to know that, we need to do the detector simulations.
Simulation studies are needed to optimize various parameters chosen for the detector. One can get a real feeling of working with the detector itself even before it is built. Simulation studies require a lot of understanding on the theoretical foundations of the subject. The groups at TIFR, HRI, IMSC and SINP are actively involved in this area. Besides these activities, extensive work on detector R&D, physics and simulation studies is being carried out at all the INO collaborating universities and IITs.
The development of human resources forms an important component in the INO project. Since 2008, we have been running the graduate program, which takes a few students every year and trains them for their PhDs.
We hear about LHC, we hear about many other collaborations in which India is involved, but this is India's own project.
These students will be doing their PhD work on issues that are of great relevance to the INO project.
The challenge for the INO is to build a world-class science laboratory, keeping in mind the ecological and environmental concerns, especially during the construction phase, and to actively participate in ongoing conservation efforts in the region. Scientists recognize that the study of nature's innermost working need not be at loggerheads with nature herself, and have addressed most of the issues related to the impact on the environment by this project. Controlled blasting will be used during the initial phase of the construction of the tunnel. This will minimize sound and thereby prevent noise pollution. Water and power will be sourced from outside with the help of the government without inconveniencing the local people. During the normal operation phase, the laboratory will take every step to ensure environmental safety. Forest or agricultural lands will remain untouched. The experiment is void of any toxic wastes and effluents, and there is no generation of hazardous radiation. Scientists will make sure that the quality of land and air is well maintained.
So the INO project will benefit the entire nation by enhancing the scientific manpower, there will also be some local benefits in terms of gainful employment, because you will have to source the services towards the maintenance of the INO facility, its laboratory buildings, and also one has to take care of the landscape around the INO laboratory site.
Efforts will also be made to improve the infrastructure and academic standards of the surrounding schools as permitted by governing rules. Exhibitions and other similar facilities will be arranged to enhance the scientific spirit of the local youngsters. The INO collaboration is very keen on scientific outreach possibilities, such as interactions with neighborhood schools and colleges, as well as with physics research and teaching groups from all over India. Small and short-term projects and other activities are envisaged to increase scientific awareness and temper and to involve students from all interested institutions. The INO will also be a catalyst for improvement in living standards in the neighborhood. Training students in these aspects would build up a technologically stronger nation. The detectors used in the INO will also find use in fields such as medical imaging. A project of this kind would strengthen research activities across various disciplines, which in turn would benefit humanity. We at the INO have one goal: to build an institute of world standards at par with the best anywhere across the globe. This will also open up the path to large scientific collaborations within India. We foresee the best minds to be attracted to the INO, further enriching it. The INO will also be a source of a steady stream of highly trained scientific manpower that will make India stand out on the world stage. Simply put, the INO will bring neutrinos to the forefront of science and will enable the advancement of society, physically and scientifically.